Okay, let's do a practice problem. So we've got N2 plus H2 making NH3, and in the reversible reaction, that also means NH3 is decomposing into H2 and N2. Right? When this hits equilibrium, when the rate of the forward reaction is equal to the rate of the reverse reaction, we don't have the same partial pressures across the board for each gas, but they do stop changing. So at equilibrium, our pressure of just the nitrogen to the N2 is 2.46 atmospheres. The pressure of our H2 is 7.38 atmospheres, and the pressure of our NH3 is 0.166 atmospheres. The reaction continues to happen in both directions. The only thing is that we can now calculate what the equilibrium constant is for the ratio of this to that. Okay, so typically our equilibrium constant is our products over our reactants raised to the power of their coefficients. In this case, we're using pressures, so specifically we might call this a Kp for the equilibrium constant with pressures. We also tend to write it this way because we use concentration in molarity a lot for these. But if we're using it for pressures, it looks a little bit like this. So we're using the partial pressure of each of the gases involved. If we have multiple gases in the reactants or the products, that means they're being multiplied together. If we have, no gases on the left or right side, then we would just put a 1. Okay, so if we are setting up our equilibrium constant expression, it should look something like this. Kp is equal to, our product is NH3, and we want the pressure of that. And its coefficient in the reaction is 2, so that's the exponent right here. Actually, let me color code it. All right. Our two reactants then are going down here. The pressure of our N2 should be to the power of 1. I'm just going to leave it out because to the first power doesn't do anything. And the pressure of our H2 is also down here. Should have a coefficient of 3, which means an exponent of 3. Now all I have to do is plug in the partial pressures of each of these, and I can get a value of the Kp under these conditions. Okay, so the pressure of my NH3 is this 0.166. We drop the units whenever we plug stuff into the equilibrium constant expression because they are effective concentrations or pressures. So we don't worry about the units. We just put the value in without the unit. So we start with atmospheres or molar concentrations. I'm going to keep up the color coding, so let me... made it in red there, so... 166. I don't have enough fingers to hold all these markers. 2. All right. Now on bottom. The pressure of my N2 is 2.46. I want to make sure I don't put these in the wrong places. Because they have different exponents, that could give me a wildly different answer. So to solve for my equilibrium constant, right, I just have to plug all this into a calculator. 0.166 squared divided by quantity of 2.46 times 7.38 to the third power in quantity. Okay, what I get here is about 0.0000279 with no units. Okay, now typically the values of equilibrium constants that we get tend to be either very, very big or very, very small. So you'll see scientific notation a lot. Right? So if you were looking at a problem and you got this answer, you go check your multiple choice and you don't see this, it might just be because it's written differently. So let's rewrite this in scientific notation. I want to move my decimal point to be right after the first actual number that's not a 0. Okay, so this is going to be 2.79. All right, I still want it to be the same value. So I need to multiply it by 10 to the something to put the decimal point kind of back where it belongs. All right, the number that goes up as the exponent of my times 10 to the is how many spots I moved, how many tens places I had to go to get this 2.79. I moved 5 spots, so that's going to be 10 to the 5th power. But I also have to be careful of the sign of this, because after all, this number should be very, very small. Something times 10 to the 5th is very, very big. So if this should be making the number smaller, this should go back the other way. 10 to the negative 5th is going to push my decimal point back to the left instead of making it go over to the right. So this is the value I want, right? So under these conditions, my KP is 2.79 times 10 to the negative 5th-ish, something around there. Okay, well, that's great and all, but what does that mean? What does it mean to have a KP value of 2.79 times 10 to the negative 5th? Well, it tells us something about the equilibrium that's happening. So if you think of this as a set of scales, kind of going back and forth, and let's say this hand is my reactants, hello, up here, and this guy's my products, my NH3, just reading it from left to right. So I start the reaction maybe with a bunch of reactants, maybe with a bunch of products, but this shakes out, and I wind up with a lot higher partial pressures of my reactants than my product. Okay, so that means that once everything has settled, right, and things have kind of stabilized, I still have a lot of reactants here that haven't gone to make products. All right, that shows in our equilibrium constant. After all, the part here that represents the reactants, the stuff I have a lot of still, is down here. And the stuff that represents the products is up on top of my equilibrium constant. So if I have a lot of stuff down in the reactants, that's going to make my value of the equilibrium constant smaller. Right? If I have a lot of stuff in the products, it would make it bigger. All right? So you can kind of think of it like this. I've got a bunch of reactants. And I've got some products. So my number, my answer for this should come out small. So if I go look up the KP of this reaction at 473 Kelvin, what that tells me is I'm not producing a whole lot of NH3 here. Most of my reactants are sitting here just as they are. Okay? So this tells me what the reaction is like. Okay? I can go look up a K value of acetic acid. It's basically vinegar. Vinegar doesn't stick around as just acetic acid. It actually has an equilibrium with that acid kind of together in the molecular form and broken up with the H pluses and that conjugate base. So if I wanted to know, how much H plus is actually floating around in there or something like that, I can look up the K value of that acid. It can tell me how much of that acetic acid is actually deprotonated, is actually making the solution acidic. Okay? So, there are applications to this. This can tell me, just at a glance, what my equilibrium is like. Now, in the real world, you might ask, how does that help anyone? Why would I need to know, how acidic a vinegar solution is? Why don't I just use a pH stripper, a pH meter, or something like that? That's fair. Okay? What it can be very useful for is making a reaction do what you want. Okay? So, our Kp here is a constant. It is a number. So no matter how many kind of reactants or products I start with, if I just load this reaction up with N2 and H2, that's great, but a lot of it's going to stick around as my reactants. Okay? I can start with a whole bunch of products, but a lot of it's going to convert back to reactants. And the ratio between the reactants and products is still going to be this number at this temperature. Just like a reaction rate and the rate constant, the equilibrium constant is only dependent really on the temperature. If we change the temperature, then yes, we can change the equilibrium constant. Otherwise, we come to this same ratio. Okay? Now, let's say I am a chemical engineer. It's my job to produce a bunch of NH3, all right? Maybe I'm lining this up to sell commercially. Like in this bottle of ammonia that I'm not sure if I can show the label of, but I already did. So whatever. Okay? It's my job to pump this out. But my reaction is working against me. I need this stuff to make money, okay, to sell it. All right? So if I want to make profit on this, but I'm only pumping out a little bit of this product for all of the N2 and H2 I throw into my container, that's not good for me. So I can change up like the temperature of my container that I'm doing the reaction in. There are other things I can do to mess with the reaction, to change this Kp, or to push the reaction over, and over, and keep driving it to make product against the flow of what it usually would sit at equilibrium. Okay? So, there are reasons for this. Okay? As we continue on, you will hopefully see some of these reasons kind of show up more and more and more. All right, let's do another example. So I've got H2 gas and I2 gas in equilibrium with two HIs, also a gas. So I pump in some H2 and I2 gas. I don't start with any of my product, HI, and then I let it go until it reaches equilibrium. I started with a concentration of about 1 to the 10 to the negative 3 molar of H2 and 2 times 10 to the negative 3 molar concentration of I2, and again, nothing of HI, so 0 molar concentration of HI. Okay, so I can set up an equilibrium constant expression so I can calculate Kc, right, where I've got my products on top, reactants on bottom. My coefficient is going to be my exponent, and the coefficients of these guys are just 1, so I could put a little 1 in there, but I don't need to. Then, to figure out the value of the Kc, all I would have to do is plug in these concentrations. But I have a problem. I have the concentration of one of these products, but not what my reactants lie at. So I start with these, they jumble up, the reaction happens, blah, 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 we hit equilibrium. I know how much product we are left with, but I don't know how much reactant is in here. And there should be some left. This is in equilibrium. This is a reversible reaction. There should be some reactants still in there. So if I want to be able to figure this out, I have to plug in the concentrations at equilibrium. Otherwise, this doesn't mean anything. Okay? So I've got this number I can plug in. But I'm going to need the concentrations of H2 and I2 at equilibrium before I can finish this calculation. So I need to figure out how much of this H2 and I2 I'm left with after the initial changes. Okay? So we're going to kind of use some algebra thinking for this. If we look at our reaction equation, one of these guys plus one of these guys makes two of these guys. Two of these guys could go back and make one of these and one of these. Now, if we were dealing with the masses of stuff, then the chemical that we were dealing with would matter a lot because different chemicals have different molar masses. So a different quantity can mean a different, a lot of stuff in our calculations. But we're using concentration. Concentration is all about moles per liter, all right? How many moles of H2 or I2 do we have per liters of the container that they're in? Okay, well, they're sharing the same container, so the volume's the same. So essentially what we're comparing here is the number of moles of each of these things. 1 mole of this plus 1 mole of this makes 2 moles of this. Now, do these have the same mass? Whoa, no, not even close. I is huge compared to H, okay? But that doesn't matter because I'm dealing in moles, not mass. So whether I'm dealing with H2 or I2, you can kind of think of this as I'm using the same number of moles of these to make this reaction move forward. And I would get the same number of moles of each of these if I reverse the reaction, okay? So we're going to think of this as if each of these was an X. All right, 1x and 1x for having, a coefficient of 1 and a coefficient of 1. All right, when these come together, we get 2x moles of whatever we started with. Okay, so if my x was 3 moles of H2, that would also mean I have 3 moles of I2 to get the reaction to work, and I'd wind up with 6 moles of HI total. Okay? So this is kind of an algebraic simplification of what's happening in this reaction. All right? I know that I started with none of this, and I ended with 1.87 times 10 to the negative third molar concentration of my HI. Okay? So to get from here to here, all right, I am adding 2x to my container. And I have to lose 1x of each of these to make that. Okay, so I lose the same amount of moles of this stuff, so therefore the same concentration. These two guys, minus x, and however much I lose, I gain in product. So I lose an x of this, I lose an x of this, and I get 2x of my product. Okay. That's cool, but it doesn't help me if I don't know what the x's are. How much do I subtract here? Well, I started with 0 plus 2x gives me this 1.87 times 10 to the negative third molar. Well, we can solve for that. Let's set it up like an algebraic equation. I'm going to drop my units. 0 plus 2x equals this concentration. 1.87 times 10 to the negative 3. Well, 0 plus whatever is just 0. Plus that number. Whatever that other number is, we add to it, it's just that. Okay, so 2x is going to be equal to this number. Okay, if I know that 2x is this, I can solve for just x. All right, my x is going to be 1.87 times 10 to the negative 3 divided by 2. Cool. Let's punch that in. 1.87 times 10 to the negative 3 divided by 2. I get 0.000935. Okay, in scientific notation, that would be, let's see, 9.35 times 10 to the negative 4, I believe, because we're moving past 3 zeros and then another one. Yeah. So my x is equal to, oops, 9.35 times 10 to the negative 4. 9.35 times 10 to the negative 4th molar. So if I know what x is, I know what to plug in up here. Okay, so I'm going to replace these. Now I'm going to keep it up in the corner just so we don't forget that it was there. Okay. So, plus 2x really meant plus 1.87 times 10 to the negative 3 molar, right? And minus x means minus 9.35 times 10 to the negative 4. Molar. Okay, we're almost there. Okay? Because now I know how much my H2 and my I2's concentrations are changing by to make this amount of product at equilibrium. Right? So all I have to do is take my initial concentrations, subtract out the concentration that I lose to get this reaction to reach equilibrium, right? And then I've got my equilibrium concentrations. So 1 times 10 to the negative 3 minus my 0.935 times 10 to the negative 4th is going to be 1. Oops. Minus. Don't forget to use parentheses so your calculator doesn't think it's smarter than you and do order of operations without your approval. Okay, I get about 6.5 times 10 to the 1, 2, 3, 4, 5 negative 5th molar. All right, and my 2 times 10 to the negative 3rd minus minus 9.35 times 10 to the negative 4th gives me 0.001065. Okay, I had to double check my work because it didn't look similar to the stuff I had from the textbook that I'm taking this from, but they just like to rewrite it so that everything had the same times 10 to the negative 3 part. So these mean the same thing. It's just a different way of writing the scientific notation. So anyway, we're free to plug these in now. Okay, we've got our concentrations of our H2 and our I2 and our HI at equilibrium. So all I have to do is plug them in down here. Don't forget the squared and don't forget to drop your units. Okay, so 1.87 times 10 to the negative 3rd squared divided by 6.5 times 10 to the negative 5th times the 1.065 times 10 to the negative 3rd. Make sure you don't type that in all in one string as this divided by this times this. Otherwise, it will divide these two and then multiply that. I would multiply these first and then divide by it. Or say this divided by parentheses, those two multiplied together. So let me plug this into my calculator and we will get, we should wind up with about 50.5. Depending on, what answer you look for, significant figures might round this to like 51 or something like that. But in either case, we can tell that this means that the reaction is pushing in the direction of the products. Since we have a number that is greater than 1, that means that the number on top of this fraction is winning. We are pushing in the direction of the products, all right? So we have more products relatively than reactants. But also, exponents kind of make this weird. So we don't usually say, oh, we have more products, because that might not necessarily be true. We say that the products predominate the reaction, all right? They're kind of the main focus, I guess, if you want to call it like that. So if your equilibrium constant is greater than 1, that means your products are predominating. If you have an equilibrium constant that is less than 1, that means your reactants are predominating.